Hello. So today the focus of this lecture will be the Dirac delta. And so let's start by defining what a functional is. So a functional is basically a block here that takes as its input a function from some space of functions, and as an output it produces a scalar, a real scalar or a complex scalar. Okay, so for a functional, its input is basically a function and its output is some number. This number can be purely real or it can be a complex number. So an example of a functional will be, from the things that we have studied, will be the norm. So for example, if you have the norm of some signal x of 2, then basically we have x of t, which is a function from the set of real numbers. Typically it is complex valued, and the norm will take this function, will take the magnitude squared, okay, and it will basically integrate from minus infinity to infinity, take the square root, and so it will produce a scalar, and in this case the scalar will be real valued and non-negative. So the norm is a functional it can be applied to a function to produce a scalar. So functionals can do things like this. So this is an example of a functional G1. So it takes a function h as an input, and what it does is that it produces a scalar by doing this operation. It takes h of t, which is the input function, it multiplies it by e to the minus pi t squared, and then it integrates from minus infinity to infinity. So the result of this integration will be a scalar. Okay, so this is an example of a functional, and this is its integral representation. This is how it basically interacts with its input. You give it an input, it multiplies by e to the minus pi t squared, and then it integrates to basically to produce just a number. Now, another functional will be G2. It takes h of t as its input, and it spits out the value of the function at the origin. Okay, so this will be a functional of interest to us. So again, this is a functional. You provide it with a function, and I will assume that basically 0 is in the domain of the function. And what the functional does, okay, so this is the delta. So delta here, again, I'm understanding it as a functional. You feed it a function, and it responds with the value of the function at 0. Okay, and so this will be a scalar, the real or complex, depending on the codomain of function h. Another functional will take function h and then will produce as an output the sum of the values of h evaluated at all the integers. So those are examples of functionals. Again, functional, so you feed it a function and it spits out a scalar, a real or complex scalar. Okay, let's focus on this second guy because this will be our hero today. So this is a functional that you give it a function and it responds with the value of the function at the origin. Can we express this functional in an integral form? Okay, because typically functionals, there is a class of functionals called linear functionals, and those are, can be expressed in this form, in which the functional is, it takes a function, multiplies it by some kernel, and then it integrates. So do we have something that gives this effect? Do we have a function such that you can multiply it by another function h of t, you integrate, and then it gives you the value at the origin. Okay, and so the answer to this is no, you cannot find a well-behaving function that will do this operation. Okay, and so let's basically try to understand why. So suppose that again you want something that is like this. You want something that gives you this. Okay. So suppose that we will work on you want it for any function. Okay, I mean for this discussion to be rigorous, we need to exactly define the space of functions that we accept as inputs. But again, just to make things simple, I will just think of functions that are continuous. Basically, the value of the function at 0 is 1. Okay, so this means that this should give you 1. If you multiply by this function, if it exists, and you integrate, you should get a 1. H of 0 is a 1. H of 0 is 0 outside basically the absolute value of 1. So basically the function h of t, let's take a function that looks something like this. It's a 0 here, 0 there, and it looks something like this. And at the origin, it is equal to 1, and its magnitude is less than or equal to 1. Okay, let's basically evaluate two things. So we will evaluate limit n tends to infinity, the integral of delta t h of nt dt. Again, delta t now is to be understood as a function. Okay, we don't even know whether it exists or not, but we will assume that it exists, and it gives you this what seems to be a useful property. It's basically you give it a function, it responds with the value of the function at the origin. So we will evaluate this, and we will also evaluate the integral delta t of limit. Okay, so we will basically do the limit once it's outside the integral, and another time it will be inside the integral. And what is h of nt? N is an integer, and if this is h of t, in the previous lecture we talked about time scaling, and so what is h of nt? It will be a time scaled version of h of t, and since n is a natural number, so basically it is 1, 2, 3, and so on. So h of, let's say, 3t. What is h of 3t? It will be this signal here, this continuous time signal or function, and it will be compressed, right? So h of 3t, as we said in the previous lecture, it will be something that is like this, from minus 1/3 to 1/3, and its amplitude will remain the same. Okay. So what is basically this? So h of nt, again, we have this function, and I took for granted that this function can be constructed. It is, but again, no need to waste time on this. So we have a function that is continuous. In fact, we can design this function to be infinitely differentiable, but for us, just it is continuous, and it is less than or equal to 1 in magnitude. Its value at the origin is 1, and it is basically, it has a compact support. It is equal to 0 outside the range from -1 to 1. Now, you can work with this time-scaled version of these functions, and because n is 1, 2, 3, 4, 5, and so on, those are compressions of the function that you see here. Now, if you do this integration, what is the result? By definition, again, we are trying to construct something such that this delta of t, such that when we integrate delta of t with h of nt, it will give us the value of the function at the origin. Now this function is designed to basically be 1 at the origin, and if you do time scaling, the same holds. H of 0 is always equal to 1. So by how the action of delta of t is defined or is desired, then this integral is always equal to 1. And the limit that we have is the limit of a sequence of ones, a constant sequence. So the limit exists and is equal to 1. Now, suppose that this delta of t is absolute integrable on -1 and 1. So it's like sort of, it's some well-behaving. We just want it to be integrable, not from -infinity to infinity, just from -1 to 1. If this is true and we can construct such a function, then let's see. Our integral here, because h of nt, again by design, it is equal to 0 once you go outside the range from -1 to 1. And h of nt is a time-compressed version of h of t. Then we know that h of t or h of 2t and so on, they are identically 0 outside the range from -1 to 1. So we can have our integral from -1 to 1. Now, this is the integrand, and its magnitude will be upper bounded by the magnitude of this guy and the magnitude of this. H by design has a magnitude that is less than or equal to 1, and we assume that delta t exists and it is absolute integrable. And so the upper bound here, we can have an upper bound that does not depend on n, and this upper bound is integrable if delta of t is like this. However, if this is true, if what I did here is true, and there is a delta t that belongs to absolute integrable functions from -1 to 1, if this is true, then the dominated convergence theorem is applicable, right? This is actually how we justify interchange of integration and limit. So if this statement is a true statement, then actually we can go to our basically integral here, and we can take the limit and apply it first, because the dominated convergence theorem will be applicable. In that case, what happens if you take the limit first to the inside of the integral? What is the limit of this thing as n goes to infinity? Now, by doing the limit first, we are fixing t. So for a fixed t, you are taking the limit as n gets very, very large. So if t is any positive number, no matter how small, there will be an n, small n, large enough such that n multiplied by t will be greater than 1. Right? Give me a t, give me a positive t, and I can give you an n, a natural number that is large enough such that n multiplied by t will exceed 1. And if it exceeds 1, by definition, this function we are working with is a function that is 0 once its argument is greater than 1 in magnitude. If t is negative, again, there is there exists some natural number large enough such that n multiplied by t will be -7 or minus, what we need is that it's less than -1. So in that case, the limit will be 0. Okay, so this will be 0. Again, because you fix a t, You fix a t. If t is equal to 0, that's a set of measure 0. Okay, so if t is equal to 0, that's just one point. If t is positive, then again you can find the natural number n that is large enough such that nt is greater than 1, and hence h of nt is 0. If t is negative, there is an n large enough such that h of nt, such that nt is a negative number less than -1, and so also h of this negative number will be equal to 0. Hence the limit is equal to 0. Okay, for all positive and negative h. It is not 0 if t is equal to 0, but again, that's a point. That's just a point. And integrals do not, do not care about things happening on sets of measure 0. So in short, basically, this will be 0, and the integral will be 0, which is a contradiction, right? Because if you apply the integration first, then the limit, if you apply integration, then limit, the integration will give you 1 by design. I mean, this is how we, or by the desired property of this guy here. But if we basically assume that this guy is absolute integrable, not from -infinity to infinity, which may be hard, but just from -1 to 1, it's absolute integrable on a closed bounded interval. If you have any piecewise continuous function on a closed bounded interval, it will be integrable. So if we assume that delta t is such, then automatically the dominated convergence theorem will be applicable, and we will be able to take the limit inside, but then we will get a 0. It's contradiction because 0 is not equal to 1. So what is the conclusion? This assumption here is false. There is no function L1 -1 to 1 basically that does this effect, which is you give it a function, okay, and basically it is integrated with the function to yield the value of the function at the origin. And I think you can, you can require other things, you can assume other things regarding this delta of t, and you discover that it cannot be any ordinary function. Okay? So the functional that takes a function as its input and produces the value of the function at the origin cannot be expressed as the integral of the function and some nice function here. Okay? So this is our result. However, we will take this integral, okay, as notation. Okay, so we can apply it as notation, as not a true integration, as notation, which means this effect. It is a functional that takes a function as an input, and then it spits out the value of the function at 0. Okay? But in engineering, we will actually take things further. We will actually treat this integral here, we will take this integration seriously, as if delta t is actually a function, which it is not. Okay? So this, this will be the way that we deal with the Dirac delta in this course. So the Dirac delta is best understood as a functional. So basically, so it is, we want this thing here to operate on functions in which 0 is part of the domain. Okay? And actually, something like the Dirac delta is designed to operate on a space of functions called the Schwarz space of functions. They are not just continuous and well-defined over the whole real axis, they are actually infinitely differentiable, and all the derivatives are bounded. So there is a big story here. Again, there is a big story to make this thing rigorous. But my point is, just the takeaway message from here is that delta of t is again something that is better understood as a functional. However, this will make life very complicated for us, and we will pretend as if it is a function, as you will see later in this lecture. So we will start like treating it as a function, but it's sort of a special function. So we need like to agree about like some rules of engagement, some rules to follow, so that we get correctly mathematical results. So we will take this integral and we will deal with delta t as if we are doing calculus. But of course, what we are doing is not calculus, okay? Again, because this integral at best should be understood as just a notation to mean the impact of delta on h of t, and delta is functional. It is something that takes a function as an input to produce a scalar. But this will make life very complicated, and so we need shortcuts. Okay, so basically we will try to learn together what shortcuts are basically there, so that we can employ the Dirac delta in basically in our analysis of systems and in Fourier terms and so on. So this integral again, we will take it as, or we will pretend that it is true, and we will deal with this guy as a function, although that it is not. Before moving, basically I started everything with an integration from -infinity to infinity. And what if your integral is from a to b? So it is not over the whole domain. So if your integral is from a to b, you can always use the trick of making the integration from -infinity to infinity and add an indicator. Okay, so basically your function now becomes h of t multiplied by this indicator. So this guy here is applicable with, if we have an integration from a to b, it's applicable if we replace h of t by h of t multiplied by indicator, which is 1. So this is 1. So this indicator is 1 if t lives between a and b, 0 otherwise. And if we apply the rule, delta basically samples the function at t equals 0. It gives you the value of the function at t equals 0. So this integral here, again, we will take it as if it's like a real integral, and it gives you this result. It will evaluate basically h of t multiplied by the indicator at 0. Okay, and so this will give h of 0, okay, if the indicator is equal to 1. And okay, this is a. If the indicator is equal to 1, and the indicator is equal to 1 if 0 lives between a and b. And this will be 0 if 0 is outside. So what we can say now, again, as a rule of thumb for dealing with this Dirac delta, is that if the Dirac delta is outside the domain of integration. So if 0 is not in AB, then it's sort of inactive. It gives you 0. This integration will just be equal to 0. Okay. Now I will let's agree that we will never have like a situation in which A or B is equal to 0. Okay, so we'll not basically play this game. So we'll assume always that the Dirac delta is, in our case here, it's still the Dirac delta without any shifts. We'll talk about shifts in a couple of minutes. the Dirac delta is basically either 0 is in the domain of it's interior to the domain of integration, or it's completely outside the domain of integration. And if I give you an integration like something like this, 0 to infinity delta t multiplied by something dt, you should simply say, you know, we will not accept this as valid. Okay, so we want basically the Dirac delta here, the original Dirac delta without shifts, to be either, you know, inside the domain of integration, or it's completely outside the domain of integration. If it's inside, it will give you h of 0 as if you are doing the integration from minus infinity to infinity, but it is outside, it's sort of inactive. And the way of understanding it, how inactive, it's again because you can actually take any domain of integration that is from A to B and take it from minus infinity to infinity, and just assume now that delta of t is not operating on h of t, but it's operating on h of t multiplied by the indicator. Okay. So can we talk about delta t minus t0? Again, now we are pretending as if this thing is actually a function and that it exists, and we can do simple function operations to it. Like we can time shift it, we can time scale it, and so on and so forth. Okay? So how can we interpret something like this? What is delta t minus t0, where t0 is a number? So the idea is always to try to get your stuff in the form of an integral in which the Dirac delta, without any shifts or any time scaling, is multiplied by some function. Okay, so if you want to understand delta t minus t0, what is this thing? In truth, you know, the truth is that this thing is another functional that basically operates on h of t, and now it gives you the value of h of t not at the origin but at t0. But how can we like sort of derive this, quote unquote derive this, again pretending that delta is a function and that, you know, it you can involve it in integration and so forth. So if you have something like this and you want, basically we don't understand what is the time shift, what it does to the Dirac delta, okay, let's remove the time shift. And the way to do this when you are doing any integration in calculus is simply to do a substitution and define a new variable u such that u is equal to t minus t0. And so this delta becomes delta of u, which now we pretend that we understand. And this h of t, u is equal to t minus t0, so t is u plus t0. Okay, so this will be h of u plus t0, and then dt is equal to du. Okay, now this guy, now we know that basically the delta, the Dirac delta, if you give it a function, it gives you the value of the function evaluated at the origin. Okay, so the result of this quote unquote integral will be h of 0 plus t0, which is h of t0. So we can just say now, you know, since we lowered the standard, we can lower it even more and say, okay, so a Dirac delta, it can be time shifted, and the time shifted Dirac delta, rather than giving us the value of the function at the origin, it will give us the value of the function at the shift, at the location or position of the Dirac delta. Okay, so this will be the time shift. So, you know, can we take this like to the time shift is like replacing t by t minus t0. So what about replacing the argument of the Dirac delta by a function? You know, as a special case, this function will be t minus t0, but it can be something else, maybe a quadratic function, maybe t multiplied by some positive or negative constant. Okay, so let's now try to understand what is delta of 5t. So this is the composition with the Dirac delta. Now, of course, like we need our function phi. I mean, if it's any arbitrary function, things will be very tough. So we need like to impose assumptions so that we can go somewhere. So we will assume that delta of a function of t. So again, as a simple example of 5t, it will be t minus t0. A linear function of t in which you just add the constant minus t0. But hopefully we can actually extend the range of functions that we can compose with the Dirac delta, and for the purpose of basically using this in signals and systems and so forth. We will assume that 5t is continuously differentiable, and shortly we will understand actually why these assumptions. So we will assume that whatever we put here as a function of time is a function that is differentiable, not just differentiable. The first derivative itself is a continuous function. We will assume that 5t is equal to 0 at some instance of time, t1, t2, t3. Okay. Remember that basically from our time shift, if we have delta t minus t0, it gives us the value of the function at t0. If t0 is 0, then basically we obtain the value of the function at the origin. If t0 is 7, so this is delta t minus 7, we get h of 7, right? So basically, again, it like highlights sort of, the position of the Dirac delta is what determines how it behaves in terms of evaluating the function at the position or location of the Dirac delta. And the position or location of the Dirac delta is whatever value of t makes the argument equal to 0. So here, the argument of the Dirac delta is 0 if t is equal to t0. And it is basically at this value of t that our function h will be evaluated. So we will push this further and say that, delta over 5t, what we really care about are the values of t that will make 5t equal to 0. Because if 5t is equal to 0, then those are, basically the argument of the Dirac delta will be 0. And these are the values of t that are basically important in terms of the Dirac delta. So for example, if the Dirac delta is multiplied by a function and it is integrated, then basically you get the value of the function evaluated at where the Dirac delta is equal to, where the argument of the Dirac delta is equal to 0. So because of this here, again, we can push it and say, basically our focus will be the roots of this equation. We will take whatever is inside the Dirac delta, equate it to 0. And the solutions that we have, the values of t that makes phi, the values of t that make phi of t equal to 0 will actually be the important stuff to us. We assume that the function is differentiable. We will assume that at those values of time at which the Dirac delta is, at which phi of t is 0, the first derivative at those points is not 0. Okay? And again, from, we will make an argument, and you'll see from the argument why actually we need these things. So again, we will have a function inside delta of t. So this is a generalization to the shift, to t minus t0. We'll say, we maybe actually we can push things further and have a function, but to make things tractable and manageable, we will make this function differentiable, and actually we will assume that the first derivative is continuous. We will assume that the function, is 0 at a number of points, and at those points, if we evaluate the first derivative, we get a positive or negative value and not 0. So what is the benefit of something like this? Why this assumption? Okay. So if the first derivative is a continuous function, and if the first derivative evaluated at some point is strictly positive, so suppose that the first derivative at t1 is strictly positive. According to our requirement here, it should be strictly positive or strictly negative. Let's say that it is strictly positive. The first derivative is a function that is continuous. So remember when we talked about the properties of continuous functions. If the first derivative is strictly positive at a point, then it remains strictly positive in a neighborhood of that point. So there will be a neighborhood of t1 on which the first derivative is positive. And what does it mean that the first derivative is positive on an interval? What does it mean in terms of the function itself? If the first derivative is positive, then the function is increasing. Okay, so again, by forcing the first derivative of phi to exist and to be a continuous function, it means that at a point in which the first derivative is positive, we don't just have the first derivative positive at this point. The first derivative will be positive in a neighborhood, in an interval about this point. Okay, and if the first derivative is positive, then you know that the function is increasing. And if the first derivative is negative, it will be negative in a neighborhood. And over that neighborhood, the function phi of t will be decreasing. So the trick that we did here by forcing our function to be continuously differentiable, to be differentiable with a continuous first derivative, will actually make the function increasing or decreasing about t1 and t2 and t3 and so on. So if you plot the function in the vicinity of tj, it will either be increasing when the first derivative is strictly positive or decreasing if the first derivative is strictly negative. So what does this mean? That in the vicinity of any tj, the function phi of t is locally a function that is monotonic, like this, monotonically strictly increasing or strictly decreasing, so phi of t is locally invertible. Okay, this function now becomes an injective function. Okay, so it is invertible. You know, if you know the value of the function, there is one value for t corresponding to one value of the function. Okay, so this is why we require the first derivative to be continuous. So here is the trick. To understand again the Dirac delta, we take the Dirac delta and multiply by some function. It's called the test function, and we integrate, and we try to examine what is the impact of basically this integration. Taken for granted that this guy here, delta u of h of u du, this will give you the value of h at 0. Now we have something more complicated because we have phi of t, which is a general function, but it's not very general. Otherwise, you know, we cannot move any further. We assume that it is basically, it is equal to 0 at t1, t2, t3, and so on. And basically, at the first derivative at those t1, t2, t3, the value of the first derivative is either positive or negative. So we will write down this integral, and basically for this integral, we will, again, like what I did in the on the first page that if you are integrating a Dirac delta, what you really want to do is to have the position or the location of the Dirac delta inside the domain of integration. You don't really need to go from minus infinity to infinity. So basically, if we go back here, if you integrate from minus 1 to 1, you still get the same result. If you integrate from minus 10 to minus 100 to 10 to the minus 100, so that's a very tiny interval about 0, no problem. You also get the same effect. So inspired by this, what we will do is say, okay, you know, our integral here from minus infinity to infinity, but we will simply divide it into integrals about tj for every j, you know, and remember that phi of tj is equal to 0. Those are basically the solutions to the equation that phi of t is equal to 0. Now, on each interval, so we have again something that looks like this or looks like that, depending on whether the first derivative of phi of t evaluated at tj is positive or negative. What we will do is that we do a substitution of variables. Okay, so I will take this phi of t and say that it is equal to uj. So that's a new variable. And this new variable, okay, again, we are talking here about something that happens on the interval from tj minus epsilon j to tj plus epsilon j. Epsilon j is basically chosen so that we have either this or that. So the function itself is, yeah. So again, it's this thing here is, if you have a Dirac delta, so it is inspired by this, or what I did on the previous page, that if you have something like this, okay, what if you basically take the integral not from minus infinity to infinity? So this is h of t0. What if we do something like this, from t0 minus epsilon to t0 plus epsilon, delta t minus t0, h of t dt? Well, you can say, you can take an integral from minus infinity to infinity, have h of t, and then have an indicator, and here you have t0 minus epsilon, t0 plus epsilon, okay, dt. And so what will be the impact of this Dirac delta? It will evaluate this function at t0. So if you put t equal t0, the indicator function will be equal to 1, and h of t will become h of t0, and so this is also equal to h of t0. So again, we will take it as, you know, again, it's not something that we do rigorously, but it is something like sort of inspired by this. If you have an integral involving the Dirac delta, you can always limit this integral to be around the position of the Dirac delta, and you will get the exact same effect. Okay, so again, if you do this or you do this, it's the same thing. You will get the value of the function evaluated at t0. So we will take it that wherever the argument of the Dirac delta is 0, so this is 0 when t is equal to t0, then that's basically what is important. We can do the integration in this particular case from t0 minus epsilon to t0 plus epsilon, and it is equivalent to this one. I am doing the exact same thing here. The difference is that we don't necessarily have phi of t equal to 0 at one value of t. We will assume that it can be equal to 0 at multiple values of t. And so rather than having just one integral, of course, you know, in the special case in which phi of t is, say, a linear function, then it is equal to 0 at just one value of t, and we don't have a sum, we just have one integral. But we will make this general and say that if there are multiple values that make phi of t equal to 0, we will simply split our integral into integrals around each one of those values of t that makes phi of t equal to 0. And this is the inspiration, which is integrate from minus infinity to infinity is equivalent to integration from t0 minus epsilon to t0 plus epsilon for some positive epsilon. And this positive epsilon, by the way, can be any arbitrary small positive number. Okay. Here, our epsilon should basically satisfy the property that a function is monotonically increasing or strictly increasing or strictly decreasing, so that we can do this change of variables. We can take phi of t, which looks like this locally. So here we are talking about local invertibility over a tiny neighborhood of tj. It's either increasing or decreasing, and we will do the substitution that phi of t is equal to uj. Now, if phi of t is equal to uj, you can say that t is equal to the inverse of uj, right? And this will make sense because those functions are invertible in the sense that for a given phi value, there is one and only one value of t giving you this value of the function. Again, like if you basically intersect this function with any horizontal line on this interval, you will just get a single value of t corresponding to the value you are talking about. So the function is locally invertible, and for the function to be locally invertible, we needed, again, this is not something that happens for any function, we needed this assumption, that phi of t is continuously differentiable, which means that it is not only differentiable, the first derivative itself must be a continuous function. Moreover, the value of the first derivative at those t1, t2, t3 must be strictly positive or strictly negative. Otherwise, basically my argument here will fail. But if my argument is okay, then the function is locally invertible, and you can write down the inverse is defined as a function. So you can do substitution of variables, and then you basically go to the rules of calculus and do this change of variables, okay? And this is what you will get. So rather than writing your stuff in terms of the dummy variable of integration t, you will write it in terms of uj. And the relationship is that phi of t is equal to uj. And so this is basically the integral that we get after the substitution. And we did this so that inside the Dirac delta, we have a variable, a linear variable, uj, just uj. Okay, so we want things to look like, the original Dirac delta that is basically interacts with functions, evaluating those functions at the origin. Okay, so we started with this delta phi of t, where we can have a complicated function here, but it should obey those guys. Now we are talking about a delta that is of some variable, the dummy variable of integration. And so what is basically this integral? What will be this integral? You apply the rule. If you take an integral, okay, and then there is a delta, the first thing you see, well, is my integration actually involved, does it contain 0, right? So we said, like, the Dirac delta is okay if you integrate it not from minus infinity to infinity, but from a minus to a plus. Any negative number to any positive number. It will be okay. So do we have this here? Do we have this situation here? Okay, let's proceed carefully. So when you do this substitution, you replace phi of t by u of j. What is the value of the lower limit of integration? So again, this is the substitution. Let me change the color. uj is equal to phi of t. So at t equals tj minus epsilon j, uj will be phi of tj minus epsilon j, which is this guy. If t is basically tj plus epsilon j, the value of u will be phi of tj plus epsilon j. And what do we know about those values? One is positive and one is negative. Why? Because the function phi of t locally looks either like this or like that. And why is this the case? Again, the story is in these steps. At tj itself, the function phi is equal to 0. At tj, the derivative of the function phi is either positive or negative. The derivative of the function phi is a continuous function. So if the derivative is positive at tj, it is positive in a neighborhood of tj. And if it's negative at tj, it's negative on a neighborhood of tj. So the function itself is either monotonically or strictly increasing or strictly decreasing in some neighborhood of tj. So if you do the substitution u is equal to phi of t, then the end points of your integration limits, you know, the integration limits, the lower and upper integration limits, will become, one of them will be positive and the other will be negative. And again, this is thanks to the assumption. If you do not assume that the derivative, that phi is differentiable and that its first derivative is continuous, you cannot make such an argument. But because phi of t is continuously differentiable, then we can do this. And yes, uj is equal to 0. Okay, uj is phi of t. uj is equal to phi of t. Okay, so it is basically, it passes through 0. It passes through 0. And you can apply, you know, the trick of the Dirac delta, which is, okay.
Doctor, sorry to interrupt you. Is it sufficient to have phi of t to be only differentiable, like first derivative differentiable, and not?
Yeah, if we are not sure about the first derivative being a continuous function, you know, so what if the first derivative is, you know, it has points of discontinuity? Then the function, you know, if a function is discontinuous, it can be positive at a point, right? It's not necessarily positive in a neighborhood of that point, right? Because you can have a discontinuous function that is, let's say, negative, and then it jumps to some positive value. So this is the level 0. It's positive here, and then it is negative everywhere else. So this is a discontinuous function. In a neighborhood of this point, the function is positive at a point, otherwise it is negative. I want phi to be positive on an interval so that I can say that, I want the first derivative of phi to be positive on an interval so that I can say that the function itself is increasing on that interval. Its first derivative is strictly positive, and so the function is strictly increasing. I do not have this without assuming that the first derivative itself is a continuous function.
Doctor, what if, like, we have it first differentiable, it's just not second differentiable? Is it sufficient to have it only first differentiable?
No, you need by the way, I didn't assume that it is differentiable twice. What is needed is that the first derivative, when you differentiate the function, the first derivative itself as a function is continuous.
Okay, thank you.
Continuity does not imply differentiability. Okay, so basically, I mean, a function that, like the absolute value function, like this. Classically speaking, you know, this function is not differentiable. It's continuous, but it's not differentiable at 0, right? So I am not required. If I require that the function is twice differentiable, this is a stronger assumption. Because if the first derivative itself is differentiable, then it is actually guaranteed to be continuous. And more than this, it is continuous and we can differentiate it again. But can we assume that the function is just one-time differential? No. You cannot guarantee that you have basically local invertibility. Okay, so basically once you have the Dirac delta like this, you can just go here and there and do the trick of the Dirac delta, which is if you combine a function with the Dirac delta at the origin under the integral sign, you get the function evaluated at the Dirac delta, at the location position of the Dirac delta, which is 0. Now we have just delta of uj. And so we basically take those guys and evaluate them, replace each uj by 0. Okay, so we replace each uj by 0. Just as a technicality, because there is a possibility that our function is decreasing. Now, what happens if you do a substitution of variables in an integration and u is equal to phi of t and the function is decreasing? Now, the lower limit of integration will be positive and the upper limit of integration will be negative. So to make the upper limit higher than the lower limit, what is the rule for integrals? If you have an integration from, let's say, 1 to 0, you can make it an integral from 0 to 1, right? But you should add a negative sign, exactly. And so if the first derivative is negative, and to make basically the upper integration limit higher than the lower integration limit, we will have a minus sign. So the trick here is basically to integrate from the negative guy to the positive guy always, and to take the extra minus sign, and the extra minus sign will occur when the first derivative is negative. So this minus sign combined with the negative first derivative will make basically a positive quantity. So again, this is the technicality. What if the derivative is negative? What we can do is that we can integrate from something that is negative to something that is positive, and we have an extra minus sign. What is the impact of this extra minus sign when the derivative is negative? We can combine this negative sign with the negative derivative and just use the absolute value of the derivative. So if the derivative is positive, we are good. If the derivative is negative, it's multiplied by a minus. And so if you have a number that is negative, minus 5, you multiply by a minus, then that's 5, which is the absolute value of minus 5. Okay, so this is a way of basically combining these two guys together rather than like having two cases that are separate. And again, finally, the Dirac delta operating on those guys, you replace uj by 0. Now, what is phi inverse of 0? Okay, so we have on our intervals, we have the function that looks like this, or the decreasing version. And so this is u, which is equal to phi of t, and this is t. When is u equal to 0? When t is equal to tj. So phi inverse of 0 is just equal to tj. And now we can express our result in terms of tj. TJs, I mean, what are those guys? They are not arbitrary guys. Those are the roots or the solutions to the equation that phi of t is equal to 0. And it must be the case for our argument to work that the first derivative evaluated at those points should be strictly positive or negative. And actually, you can see that when you do the change of variables, that you will get the first derivative in the denominator. Right? So this is like sort of after the fact justification, right? So we got this guy here. Definitely we don't want this guy to be 0, else we are dividing by 0. We want it to be strictly positive. Okay, so again, this confirms that the need that the first derivative evaluated at those points should be strictly positive or strictly negative. Okay, so let me basically recap what we did. So we took this integral h of t dt, and we showed that this integral is like this. Under some assumptions, right? And of course, like, you know, we pushed things, right? So for example, we started with the integral and then we said, okay, so we know, okay, we will take it like sort of for granted that the Dirac delta is quote unquote active whenever its argument is equal to 0. So let's go equate phi of t to 0 and find the points at which phi of t is equal to 0. And now let's, rather than integrating from minus infinity to infinity, let's have integrals, a sum of integrals over intervals about t1 and t2 and t3 and t4. And basically the intervals on which we do the integration are chosen such that the function phi on those intervals is strictly increasing or decreasing, meaning that it is locally invertible. And we got this result here. Okay, now what is tj? I can take this h of tj and rewrite it as the integral from minus infinity to infinity delta t minus tj h of t dt. So we got the value of the function h evaluated at tj, which is the effect that we get if we basically couple this function with the shifted Dirac delta under the integral sign. Now, if we assume that we can interchange summation and integration, then this can be written as integral from minus infinity to infinity, summation j delta t minus tj over phi of 1 tj, like this, multiplied by h of t dt. So we started with this integral, we ended up with this integral. So we will take it as a matter of equality. The delta of phi of t, which is this guy, when we compose a function phi of t with delta, then this is what we get. The effect of composing a Dirac delta with some function phi, of course, that is nice enough, continuously differentiable and has those properties. The effect is that we generate a number of Dirac deltas, not just one. The number of Dirac deltas depend on how many times the function phi of t crosses the horizontal axis. In other words, the number of Dirac deltas will depend on the number of solutions to the equation phi of t is equal to 0. We will get those Dirac deltas at the times at which phi of t crosses 0, and we get some additional thing. Those Dirac deltas will not just be shifted. Each one of them will be scaled in amplitude by 1 over the absolute value of the first derivative of the function phi at tj. And remember that this guy is assumed to be strictly positive or negative, so we are not dividing by 0. Okay, so this is how we will define or take the composition with a Dirac delta. Let me write it again. It is a nice expression. So this phi of delta of some phi of t that again that obeys some conditions. It is delta of t minus tj with a sum. And what is tj? Those are basically the guys that make phi of t equal to 0. So we have a bunch of Dirac deltas. If basically phi of t is 0 at 2 values of t, then we have 2 terms in this sum. three values of t, we have three terms, and so forth. So we got shifted Dirac deltas, and each Dirac delta is scaled in amplitude by this value. Okay. So let's now go to special cases of phi of t. So now what can we say about delta of at plus b? So now we have a linear function where a is not equal to 0. So at plus b is equal to 0. This is like phi of t now. It's equal to 0 at how many points? Just 1 point. At t is equal minus b over a. So what is our derivation telling us? It tells us that delta of at plus b is one Dirac delta. It's just one Dirac delta. And it's living here at this shift minus b over a. And it is scaled. What is this amplitude scaling factor? It is 1 over the first derivative of this guy. And what is the first derivative of this guy? It is a. And a can be positive or negative. We need to take the absolute value. So this is basically this Dirac delta. Dirac delta of at plus p is delta of t plus p over a. It is a shifted Dirac delta, and then you need to scale by 1 over the Dirac delta. Now, at a special case, what if you put b equals 0 and a equals minus 1? If b is equal to 0 and a is equal to minus 1, this thing will be 1 over the absolute value of minus 1, which is 1, and b over a will be 0. So delta of minus t, which corresponds to this special case, is delta t. So again, since we lowered the standard and now we are treating the Dirac delta as if it's a function, well, if it's a function and we will keep doing this for convenience, it is an even function. If we treat this as a function, it is an even function, and this will be important like when we involve the Dirac delta in Fourier analysis, because the Fourier transform of functions will depend on their symmetry. Even functions transform in a certain way and so forth. So delta t is an even function, and if you put b equals 0, and so you just have time scaling. So the time scaling of a Dirac delta can be converted into an amplitude scaling. Delta of at is delta of t, and you just divide by the absolute value of a. Now let's go a bit more. This is actually the objective of the previous slide, is that can we have a Dirac delta of a quadratic function of t? So it turns out that yes, this can be defined not for every quadratic function, but for many of them, as we will see. Now, for the quadratic function is different from the linear function. The linear function is guaranteed to cross the horizontal line at one point. The quadratic function, basically, you may have a parabola that looks like this. The quadratic function may not have real roots, right? This equation here may not have a solution on the set of real numbers. In that case, the argument of the Dirac delta cannot be made equal to 0. So we will assume that the Dirac delta is quote-unquote inactive. It is dead, okay? It is 0. So if you take it, multiply by a function, you get 0. It's as if it's not there. So this is one situation. Another situation for the quadratic function, define it. You need definitions, right? So so if you have a delta, delta of a complex, what does it mean? You need to define it. You need to come up with a mathematical basically a definition of what does it mean, like to have a complex number inside the Dirac delta, right? So we don't care about the values here. Again, yes, this thing, if we cannot make it zero with real numbers, we can just use complex numbers. And it has actually two complex roots. But again, from the point of view of a Dirac delta, Okay, for now we are defining it to have a real argument. Okay, so and it acts on functions. The functions may be complex valued, but their argument, which is t, is purely real. Okay, and by the way, this also applies to the Fourier analysis. The parameter of Fourier analysis, which is f, the frequency, is real. Okay, so we can basically change this by like doing the Laplace transform, in which we allow the variable to be complex value, but we are not doing this right now. For now, t is real value. Our functions of signals and systems now, they are x from a real value parameter t to complex numbers. So the function can be complex value, but t itself, t is real, period. Okay, we do not allow complex times or something like this. Now, if the parabola looks like this, then the function has a repeated root. In this case, we have a problem. What is the problem? Let me just talk on, does this make sense? Delta of t squared. What is the problem of t squared? T squared equated to 0. T squared equal to 0. This is 0. This is 0. Repeated roots. It is, but actually there is something else. What is the first derivative of t squared? D by dt t squared. It is equal to 2t. And what is 2t at t equals 0? It is 0. It violates our assumption that if the function phi of t is 0 at a point, its first derivative at that point must be strictly positive or negative. So this will be violated if we have a repeated root. So what is basically, what should we do? Rejected. We will not have this. Rejected. You cannot have delta of t squared. By our rules of engagement, this is something that we should not use. And in any situation in which actually we have a quadratic with repeated roots. But here is the good news. If our roots, we have two real solutions, you can show that the first derivative, so basically ap squared plus bt plus c, it has two roots. It has two real roots if the discriminant p squared minus 4ac is positive, and you can check that the first derivative will be 0 at minus p over 2a. So the first derivative is 0 at points that are different from t1 and t2. So in that case, the first derivative is a linear function, which is a continuous function, and the first derivative is not 0 at t1 and t2, and we have everything on the previous slide satisfied. So in this case, if the discriminant is greater than 0, and so we have a parabola, that looks like this or like this, we have two real roots. The Dirac delta operating on a quadratic is actually a couple of Dirac deltas at the two roots of this quadratic, and they are scaled. And the rule is that you scale by 1 over the absolute value of the first derivative evaluated at basically those points that make this equal to 0. Okay, so as a special case, if we take t squared minus 1, this is our function phi of t. So the first derivative is equal to 2t. When is this function equal to 0? So phi of t is equal to 0 if t is plus or minus 1. And the first derivative, phi 1 of, so basically the first derivative evaluated at plus or minus 1 is plus or minus 2, not equal to 0. We have everything satisfied, and so this Dirac delta will be the two Dirac deltas living at wherever values of t make t squared minus 1 equal to 0, and there will be this amplitude scaling, and it is by 1/2 because if you put t equal plus or minus 1 and take the absolute value, you will find that the first derivative is equal to 2. Okay, so we can do these things. We can do other things, that we will see later. It's okay, and so on and so forth. Okay. What if we multiply by Dirac delta? Okay, so in some applications, like when we study the conversion between discrete time signals and continuous time signals, we typically model the sampling process as if we take a function and multiply it with the Dirac delta without integration. So how can we understand something like this? Again, the idea is study this quantity with integration and see what it leads to. So take this quantity, multiply by this, the so-called test function, and see what happens under the integral sign. If you integrate this thing here, what is the result? You can rewrite the integrand as the integrand of the Dirac delta multiplied by this guy. What is the rule? The rule is that the Dirac delta living at t0 will evaluate this function at t0. So this is x of t0, h of t0, right? But if you have x of t0, h of t0, you can take this h of t0 and rewrite it as integral from minus infinity to infinity, delta t minus t0 h of t dt. And this is just a scalar. So we can write, again, let me write it like this. So we can write this on the test function h of t as this. So we will take it that a function multiplied by Dirac delta is the Dirac delta with multiplied by the function evaluated at quote-unquote the position or location of the Dirac delta. Okay, so this is basically the trick. So x of t delta t minus t0 is basically x of t evaluated at t0 multiplied by the Dirac delta. The Dirac delta will not go away. It goes away if we have integration. If we just have this multiplication, then the Dirac delta will remain as is. It is just that if you have x of t multiplied by Dirac delta, then basically you can replace this function x of t by its value at the location of the Dirac delta. And if the value of the function at the Dirac delta is 0, this is equal to 0. Okay, so let's give an example. If you have tx of t, what is this thing? T delta t. So you evaluate t at 0. So this is 0 delta t, 0. Okay, so if the function multiplied by the Dirac delta is 0 at the location of the Dirac delta, then you have a 0. Then the whole thing that you have is equal to 0. And of course, the assumption is that, of course, here is that t0 has a value, and so it means that t0 is part of the domain of this function. Can we differentiate the Dirac delta? It is designed in mathematics, in the theory of distributions, actually to be infinitely differentiable. Just differentiable. It can, you can think of it as infinitely differentiable. Let's do things in the non-rigorous way. So, can we define something like this? I use this superscript as the first derivative, as I did earlier. Can we define basically a derivative for the Dirac delta? Suppose that this is true, and if you see an integral like this with ordinary functions, what will you do? You typically, if you have like the derivative of one function, you are motivated to do integration by parts, right? So let's assume that we can actually do this here, and we can, so again, we are pretending that we can deal with the Dirac delta as if it's as if we are doing ordinary calculus. And so I will just move it like this, do integration by parts, and we'll assume that this quantity is 0, assumed 0. Okay, so you know, I cannot like argue rigorously that it is 0. It's assumed to be 0, okay? Then basically when you do the integration by parts, this will be minus integral from minus infinity to infinity delta t dh of t. And so again, you apply integration by parts, so this will be delta t multiplied by the first derivative. And there will be a minus sign that comes from integrating by parts. So we have our old friend here, the Dirac delta. And what is the impact of the Dirac delta when it's coupled with the function under the integral sign? It evaluates the function at the origin. So basically, this will give you minus the first derivative of h of t, assumed to be differentiable once, at 0. So we can take this to be a rule, that the impact of the first derivative of the Dirac delta with a function under the integral sign will be a negative, and then the first derivative of the function evaluated at 0. And if the derivative of the Dirac delta, you know, you can basically push this to any order of differentiation. So so basically you can start with this thing, and you assume that you can repeatedly do integration by parts. So in that case, we will take the delta of, so this is the nth derivative of the Dirac delta, okay, and its impact on h of t, which can be derived, quote unquote derived, using integration by parts, is basically that you evaluate the function, not evaluate the function, evaluate the nth derivative of the function, assuming of course that it exists at the origin. And then there will be a minus 1 to the power n, because when you do the integration by parts, at each step there is a minus sign that will be flipped. And you extend this to shifts. So if you have a shifted derivative of a Dirac delta, you can assume that now when you evaluate the nth derivative of the function, you don't do this at the origin, you do this at the location of the derivative of the Dirac delta. So can we differentiate the Dirac delta? Yes. In fact, in distribution theory, the Dirac delta is designed to be infinitely differentiable. And the impact of its derivatives is to evaluate not the function, but to evaluate the derivative of the function. And then there is an annoying minus 1 to the power. And here again, because things happen as if we are doing integration by parts, and so we have this minus 1 to the power n. Okay, so so now again we learned today about before going to the last slide, that we have so this is meaningless, meaningless. Okay, so this is meaningless. If basically there is no differentiation, then this is meaningless. Okay, and so basically in the theory of distributions, when we apply the Dirac delta, we apply to a class of functions for which everything that is written here is satisfied. So you can read about the Schwarz space of functions. No, say it again. Why the first, we cannot do so. Here you need the first derivative, the function to be differentiated n times, and I am assuming that it is differentiable on R, and so basically its derivative is on the whole of R, so it's defined at 0 or at t0. No, not needed. No, it's not needed. For h of 0 to be 0, is not needed. Basically, what you need h of t is that it's behaving gently at plus or minus infinity, so that you can justify basically setting this guy equal to 0. But h of 0 itself, it can be any. So basically, delta of t, applied to h of t, it will give you h of 0. Applied to, the first derivative of the Dirac delta applied to h of t will give you minus the first derivative of h of t evaluated at 0. The second derivative of the Dirac delta applied to h of t will give you the second derivative of the Dirac delta at t equals 0, and so on and so forth. Okay, and we are assuming that, again, those derivatives actually exist. If they do not exist, then you are writing something that is meaningless. You are writing a derivative of a function that is not even differentiable. Okay, so now we know that we have delta g of t. We have a formula for this. It's not true for a or phi of t. It's not true for any phi of t. It requires conditions. Okay, and it is useful because it allows us to compose some function with the Dirac delta. Now we also know that this guy here is meaningful, designed to be meaningful. The nth derivative of the Dirac delta with respect to t. Okay, and this guy, again, if the Dirac delta evaluates the function, its nth derivative will evaluate the nth derivative of the function with an annoying -1 to the power n, again, based on basically the fake derivation that we have here. And even in rigorous derivations, there is also integration by parts, and you will get this -1 to the power n. So it is not like totally false. It is true that we have this -1 to the power n there. Now, what about x of t multiplied by the nth derivative of a Dirac delta? So remember that what is delta t multiplied by Dirac delta without integration? What happens here is that you evaluate the function at the position of the Dirac delta, and the Dirac delta remains intact. You do not remove it. It disappears when you do integration. What about multiplying a function by a derivative of the Dirac delta? Okay, so things will be a bit more complicated. So we'll do this in the next lecture, but to give you a flavor of what's going on. So basically, when a function is multiplied by a derivative of the Dirac delta, the result is basically a summation with a number of terms equal to n plus 1. So if you multiply x of t by the nth derivative of the Dirac delta, generally you get n plus 1 terms and not just one term like here. Okay, so this will be a bit more complicated. And again, to understand it, we will do our trick, which is take x of t multiplied by this guy, multiplied by a test function dt, and see what this thing, basically, try to simply play with it, simplify it, do things, pretending that you can apply ordinary calculus, and then you will see the impact of x of t. And then our case here, again, we will get a bit more complicated expression for the product of x of t multiplied by the nth derivative. So the last thing to say in this lecture is, so we'll do this like in the next lecture, but like, can we have something like delta t squared? No. You cannot multiply a Dirac delta by a Dirac delta, or delta t minus 1. No. You cannot do this. You can multiply Dirac deltas if their arguments are different. Okay? So in 2 dimensions, in 2D, for example, the Dirac delta, you can write down something like this. So long as x is a coordinate and y is basically the other coordinate, this is okay. And actually, it's the definition of the multidimensional Dirac delta. But Dirac delta with the same argument, this is nonsense. And in this lecture also, we said that something like this also is not accepted. But something like this, delta t squared minus 1, this is okay. Again, because this is an example of a quadratic inside the Dirac delta that has 2 real roots. And so we can actually convert this Dirac delta into 2 shifted Dirac deltas that are amplitude scaled.